So we've seen that omega, capital N comma n, is equal to n factorial, capital N factorial, over little n factorial times n minus, times big N minus little n factorial, with omega total being 2 to the n, right? So we can imagine having n coins and the coin can come up heads or tails, and so we can ask, what is the probability of having little n, right? So that becomes n capital N factorial over, so it's this expression divided by all of the possible states. So we have 2 to the minus n, right? We divide by this. And right, not immediately obvious that this kind of a system is found in the physical world, and we'll see that it is, so these statistics are very useful. But if we start playing around with the numbers here, right, as soon as n, if we're dealing with a number of molecules, a gas, or some kind of material, these numbers are huge, and it becomes impossible to deal with these numbers. But we also know that if we have coins and we start to flip these coins, we'll know that we'll tend to get, if we do this many times, we'll start to get half heads, half tails, right? And if we have many such coins, we kind of know what that distribution will look like. It will be a Gaussian distribution. So what we want to do now is show that the kind of numbers that we get here, the kind of distribution that we get, is just a bell curve. So let's say that we have little n is equal to, right, so number of tails or number of heads is, half of them are heads, but we have a little bit more than that. We have some x additional. This is maybe some small number compared to that one. For simplicity, let's just divide that by 2. It'll be convenient. So we have some additional number of heads. So x over 2 more heads than tails, right? And so we want to ask what kind of a probability are we dealing with here? So this kind of expression becomes p of x comma n. That looks like n factorial over this now is this, so we have n plus x over 2 factorial times n minus x over 2 factorial to the 2 times 2 to the minus n. And let's use the Stirling approximation. Again, it's impossible to get actual numbers out of these factorials because they're just too big. So let's use the Stirling approximation, and we'll actually be able to derive the Gaussian from this kind of object. So the Stirling approximation has, we have a big number, a, and we're doing a factorial, and so we get a to the a. We can derive this expression, but we're just going to take it for now. E to the minus a, 2 pi a square root. So this is for large a. And so we're going to end up with a probability which is approximately square root of 2 pi times n to the n, square root of n, e to the minus n, 2 to the minus n, over square root of 2 pi, square root of n plus x over 2, n plus x over 2 to the n plus x over 2, e to the minus n plus x over 2, square root of 2 pi times n minus x over 2 square root, n minus x over 2 to the n minus x over 2, e to the minus n minus x over 2. Okay, so in the next video, we'll continue with this expression, we'll narrow it down, and we'll see that we'll get a Gaussian.